Today, I would like to talk about the different types of chemical bonds. So you can think of there being three main categories of chemical bonds that you'll see in everyday use. So first is an ionic bond. The second is what we call a covalent bond. And the third is a metallic bond. Okay, so let's talk a little bit about these different types of bonds. So an ionic bond involves the transfer of an electron, and I will go into more detail about these in a moment, just want to briefly touch on them first. A covalent bond involves the sharing of an electron, and a metallic bond, you might have heard of this as called as the electron sea. And that's whenever electrons in metals, they have a tendency to kind of dissociate from one metal atom in particular and be shared throughout the entire metal. And that's actually kind of where conductivity comes from. So for this video, we're going to mostly focus on these two here. So I'm just going to erase this one for now. Okay, so let's talk about an ionic bond. So an ionic bond is when one of the electrons is transferred, or at least one I should say, is transferred from one atom to the other, forming ions. So we can see this if we have something like, let's see here, if we have sodium chloride, we can look at our periodic table, and so sodium is a group 1 element, so we know that in its it has one valence electron, so we're just going to draw a Lewis structure of sodium here. It has one valence electron. And then chlorine, it's a group 18, or 17 rather. It's a halogen, so it has 7 valence electrons. So this is the neutral atoms. So this is one electron short of being a full octet. And if we lose this electron, that's the only thing in this shell, so then it'll be a full octet. Because you can see, which I'm not sure how well you can see on this periodic table here, but if you lose an electron from sodium, then you'll have the neon electron configuration, or that noble gas stability. And if you add an electron to chlorine, you'll have that argon electron stability. So you have a noble gas electron configuration. So if we take this electron and we're just going to move it over here, then that will give us sodium plus, because it lost an electron has a -1 charge, so if you lose a negative charge, then you have a positive charge. And that will give us chlorine minus, because it has gained an electron, so it's no longer a neutral chlorine atom. So now we can just look at electrostatics and say, well, we have a +1 charge here and a -1 charge here. So this negative density, or this negative electron density, is going to go and bond with this positive to form sodium chloride, the salt. So that's an ionic bond, is when an electron is transferred from one to the other. So ionic bonds are pretty strong because they're this nice charging capability. Now let's talk about covalent bonding. So covalent bonding, I think you probably have seen a lot of examples of by now. So we can look at just a very simple case. So if we have like a carbon, it has some electrons, we have another carbon over here. Let's say they're bound to hydrogens on either side, just to fill up their octets. I'm just going to draw these Lewis structures. I'm going to neglect drawing the lines here for right now, and just draw the dot structure. So you can see each of these carbons has 7 electrons by it if they're not bound to each other. But if they share, let's draw a circle around all the electrons. If they share these electrons, then this has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This has 1, 2, 3, 4, 5, 6, 7. Oh, actually, let me draw a circle through that one. So that's 8 electrons. So they both have that noble gas electron configuration. They have a full octet, and they're nice and stable. So they share this electron density. And now, if you had siblings, you might know that sometimes when you're told to share something, it's not exactly a 50-50 split. So in this case, it will be, because the carbons are electrically identical. So if you look at the electron environment here, they are all bound to hydrogens, and they're bound to each other. Carbon is bound to, so this is called a methyl group. So it has a methyl group on it, and this one is also bound to a methyl group because they're identical. So they're both going to be exerting the same attraction towards that electron. Now, if you remember, there's a concept called electronegativity. And electronegativity is just the atom's ability to pull electrons towards itself. And the periodic trend for electron negativity is that it increases as you move up a column and down a row. So let's say if we had something like hydrogen chloride here. So what kind of bond will this form? Well, chlorine is a lot more electronegative, so it's going to pull this electron a little closer to it. So let's just draw that little arrow there. So it's going to be, it'll still share it, but it'll be a lot closer to the chlorine. Here, I'll draw the rest of the valence shell there. So this chlorine is actually going to have a partial negative charge because that electron is going to be closer, it's going to be more associated with that chlorine than with the hydrogen. So then the hydrogen will have a partial positive charge. And for a review, this symbol here, this is gamma. And you can think of it as meaning partial. So it doesn't have a formal positive charge or negative charge, but it has a partial charge. So what that means then is that this whole system is polar. And in this case, because it's just a linear system, the dipole moment will be through the atom itself, like that. So this here is a polar covalent bond. And then what you call bonds that don't have this characteristic, such as this one up here, is simply nonpolar covalent bonds. So now you may be thinking, well, how do I know? You know, like how much of a difference in electronegativity does it take for a bond to be polar or nonpolar, or even for the bond to be strong enough, or for the difference in electronegativity to be strong enough that it's going to pull that electron all the way away? Well, there's actually a nice way that we can think about this. So we can make a little chart here. So if we have a number line, and this number line is the electronegativity, and this is actually the difference in electronegativity. So you take the electronegativity of one of your atoms, and then just subtract the electronegativity of the other one. And this is in Pauling electronegativity. It goes from 0 to 4. So fluorine is the most electronegative element. So it has electronegativity of 4. So that's where we set the scale. So if you take that, and you just take the absolute value, so it's all positive numbers, then you can look, and on here, so we'll have over here at 2, then over here at, I believe it's 0.4, although I'm blanking on that. Let me check my notes here real quickly. Yes, it's 0.4. So if the difference in electronegativity is greater than 2, then that's what we would call an ionic bond. And then if it's below 0.4, then the difference is negligible in terms of the dipole moment. So that would be a nonpolar covalent. So then I bet you can guess what is in this middle region, and that would be the polar covalent. So that would be when the difference in electronegativity is such that the more electronegative atom is pulling that electron density away from the least electron negative atom, but not enough that it just outright takes it. So, so if you're asked what the difference is in electronegativity, or what kind of bond it is, you can simply look up the electronegativity of that atom, and you can just take electronegativity of atom. If you have atom A bound to B, the formula for the difference in electronegativity is, you can say the electronegativity of A minus the electronegativity of B, and take the absolute value of that, and then you can just plug that into here, and that'll tell you what type of bond it is. So if there's any questions about this, feel free to leave that in the comments section down below, and I will do my best to respond to all comments. And if you have anything that you would like me to go over in future videos, please feel free to leave that down below as well, and I will do my best to respond and to provide you the content that you want, so that everyone can learn about chemistry. So, thank you. Have a good rest of your day. Thanks.